A and B are two material points on a rigid body, then we can relate their velocities, right? VB minus VA is equal to what? Anyone remembers? If A and B are two material points on a rigid body, VB minus VA is what? Yes. Exactly, RB minus RA or XB minus XA. Very well. And then we also considered the case where A is a material point on the rigid body and B is moving with respect to the rigid body. Okay, so this is kind of where we was left off last time. We talked about relating the velocities of two material points on rigid bodies and also relating their accelerations. And we also did that. We derived this equation if A is a material point on the rigid body and B is moving with respect to the rigid body. Okay? And these equations have the additional terms, the corrotational rates, x corrotational B with respect to A and x double corrotational B with respect to A. And these are the velocity of B, and the acceleration of B as seen by someone that is fixed to the rigid body. And we gave an example. If you're sitting on a bus and you're seeing someone moving on the bus, those would be the velocity and the acceleration as observed by you, an observer on the bus, would be the corrotational rates if you are an observer fixed to the bus. So this term is what we call the centripetal acceleration. The omega cross omega makes it that it points kind of parallel to xp minus xa. And then this Coriolis acceleration we wanted to talk about. And for that, let's watch this video. Any questions before we do that? Any questions about this?
With a simple game of catch, I think I found a way.
Okay. Hopefully you can hear it because the sound is only coming from my laptop.
With a simple game of catch, I think I found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on a specially
Can you see?
rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
All right, here's the game, right? You're going to throw the ball straight. So what's your name? Victor, right? Yeah. But this time, I'm going to complicate things slightly. I'm going to rotate to the merry-go-round counterclockwise. So you throw it whilst it's moving.
Well,
what's going to happen?
Wait a second. So they're going to throw the ball while the merry-go-round is moving. And these people, they are fixed on the merry-go-round. Now we know that when you throw a ball, what's the trajectory of the ball is going to look like? It's a parabola, right? A parabola and the plane. It's a simple projectile motion. So we know that an observer that is fixed to the earth, a fixed observer will see the true motion of the ball. That is, it's moving in the plane, parabolic motion. So top view, if you were looking at the top view, that's the merry-go-round and that's our top view. If the person here is giving the ball an initial velocity like that, then we would see the ball moving kind of along this plane. But because of the rotation of the merry-go-round, now if we look at the ball as an observer on the merry-go-round, do you think we're going to see a straight line path for the ball? No, it's going to be distorted. And that's what's called the Coriolis effect. It's due basically to the rotation of the frame and the motion relative to the frame. Let's see what's going to happen.
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah, I don't know.
Right, what's going to happen, dude?
I was going to veer off to the left.
So the ball is going to swerve off to the left.
Yep,
And you might catch it.
possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more. Spencer,
He's not arrogant.
just quietly
He's
confident.
not catching it. He's
Really?
not catching it. No,
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying comes to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across
Okay.
the spinning merry-go-round. But
So here, this view is from a fixed point of view or from the moving frame? Fixed frame or moving frame? Well, be careful.
Where will
is it
it
a
end
fixed
up?
frame? Or the ground is moving, but the merry-go-round is fixed. So here, the view is from the moving frame.
will it be caught by the thrower or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this.
So the answer was D. It was caught by the person on the thrower's right. Our camera angle seemed to show the ball bending.
Okay, so let's repeat that again. The camera angle here, notice the camera angle is fixed to the rotating frame. It's going to
Was
show
right.
this bending
Our
effect.
camera angle seemed to show the ball bend in the air. So is that a
Kind of like there's a fictitious force on the ball. That's why sometimes they call the Coriolis effect kind of a fictitious force. But it's not a fictitious force. It's just due to the rotation of the frame.
camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to shoot.
This way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all.
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight-moving ball. And it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to. And that, ladies and gentlemen, is the Coriolis effect.
Okay, so yeah, that's the Coriolis effect. Again, due to the rotation of the frame and the motion relative to the frame. Kind of like, has anyone heard of the Foucault pendulum? Maybe you've been to some museums that have it. So a lot of times in dynamics, we assume that the Earth is fixed, but in fact, the Earth is rotating. And Foucault was able to prove that the Earth is rotating because of this pendulum. So when we release a pendulum from rest, we expect the pendulum to move in a plane, right? Now what Foucault did is that he observed that the pendulum, the plane of motion of the pendulum is moving. So let me show you a kind of a video.
Completes a day by rotating for you to see. So
that's the big
any
pendulum.
direction. It takes about 8 seconds.
And at the swivel on top, the pendulum is kind of free to move in any direction. From our dynamics, we know that it's going to move in a plane. However, what we
For it to
observe,
go from there over to here and back, the law of inertia, which is going to speed things up in this video about 480 times, so that you only see the pendulum when it's at this point in its swing here. And doing that will compress the next 32 hours into 4 minutes of video. We're going to try science. Played back at this speed, the pendulum appears to move around the room, but that doesn't really grasp what's really happening, because the
why is the pendulum moving around the room? What is it? What? It's the rotation of the Earth, right? It's proving the rotation of the Earth. Because if the Earth were not rotating, the pendulum just needs to move straight. It goes straight up. But we observe it to be rotating because we are on a moving frame. And that's how they showed kind of that the Earth is rotating, okay? If we were at the North Pole or the South Pole, the pendulum would kind of switch the plane in each 24 hours because that's, well, the Earth rotates about its axis every 24 hours. Okay, any questions? So we can actually, you see the interesting animation, remember the interesting animation they had at the end of the Coriolis effect video, that one? We can try to recreate it. Let's try to do that. Okay, before we do that, let us watch, I think I had one more video. Ooh, where did it go? Well, no. Sorry. Continue without an account. We want delete profile. Gosh, guest mode. Let's go back to YouTube and we're gonna watch a Mr. Beast video now. Ferris wheel. Mr. Beast. Okay.
For refresh.
Come on. Okay, one more ad. Okay, this video we're just gonna
ride this Ferris wheel 1,000 times.
Okay, we're just gonna look at the kind of motion of the Ferris wheel. I wanted to ask you. Okay, so look at the Ferris wheels. What kind of motion are these cabins undergoing? Okay, that's a tough pick. Okay, here now, probably the slow-mo. Okay, what kind of motion are these bins undergoing? Are they rotating, just translating, or both? General motion. So think about it. Chat with your neighbors. Are these bins rotating, translating, just translating, or like both? Chat. Okay, that's a good view of what's happening. Okay, who thinks the buckets are just rotating? Raise your hand. About just. What about rotating and translating? Well, how do we settle this debate? How did we define rotation? Yes. All right, now let's think about a fixed frame. We're on a fixed frame, this fixed frame, and we're observing the merry-go-round. How did we define a rotation? Yes.
Like, just if we split out the Ferris wheel very, very fast, the cards will, they will turn outside along the radius.
Okay, they might, but they are connected to the wheel such that the cards are always, you see, in the same kind of orientation. So I do not think the buckets are rotating. Let me tell you why. If you look at a material point on the bucket, so let us say every bucket has one striped line like this. If you look at this line as the bucket moves, is this line gonna rotate or are they gonna remain parallel? Are these lines going to rotate or are they remaining parallel? They're remaining parallel. So if we look at material lines on the rigid bodies, the material lines are remaining parallel between each configuration. So then is the bucket rotating or not? No, it's just translating. But it's not the typical translation we've seen. Rectilinear translation is when an object is just moving and then material points on the object, they will trace straight lines. What's happening here is what we call curvilinear. Translation, where different point on the rigid body, they trace curves, but these curves are parallel. And during the motion of the card, its orientation is always preserved. So both of these motions are two types of translation. Another type of rigid body motion is rotation about a fixed point. Rotation about a fixed point, kind of like the Ferris wheel, but the wheel itself, it's rotating about this center point. So that's a fixed point rotation, meaning that there's a point on the rigid body that has zero velocity. Okay, and then the fourth type of motion that we're going to classify for rigid bodies is general rotation plus translation. There is not necessarily a fixed point. Okay. If we'll have time, we'll go back to the merry-go-round example, but let us continue from here. Let us draw the velocity profile of each of these motions. Okay. Well, we'll need one more video, but we'll do it later. Hide screen. Cool. Okay. So the velocity profile, what we mean by velocity profile? Is It's just basically taking the rigid body and plotting the velocities of multiple points on the rigid body, kind of to visualize the motion. So for example, for an object that's translating, maybe I'll call this A, B, C, D. For object A, if this object is going from here to here, along this, then the velocity profile of the object looks something like this. For a body that's just translating, what is omega? What is its angular velocity? 0, right? Omega is equal to 0. So VA is equal to VB for all material points. Okay? So the velocity profile here is just kind of simple. Same applies in case B. If we're going like that, still we're just translating. So what is omega in this case, case B? What is the angular velocity? 0. Okay, so velocity profile also simple. All the points, they have the same velocity. Now, it becomes more interesting when we're looking at something that's rotating. If I have, say, a bar rotating about a fixed point O, how can I draw the velocity profile of this bar? Yes? I didn't hear you. Can you say again?
So the velocities would be and then will it be smaller and you mean 0 at the point where it's rotating?
Exactly. So the farther we are from the fixed point, the higher the velocity magnitudes. How can you show that? That the more far away we are from the fixed point, the bigger is the magnitude of the velocity. Can we show that maybe using an equation we have? Yes.
With like xb minus xa being greater the farther away b is.
Exactly. So if I apply the top equation, xb minus xo, well, vb minus vo, or va minus vo. I'll take some point A on the rod. Va minus vo is omega cross xa minus xo. So here omega is that. So the angular velocity omega is out of the page. So then what is the direction of, well, VO is 0, right? So what is the direction of VA from the cross product? It's perpendicular to omega, so it's in the plane, but it's also perpendicular to what? XA minus XO. So that's XA minus XO, or XA with respect to O, and then VA is perpendicular to that. Okay? Now if I take point A to be at the end, what is the direction of VA? Or just look at point B at the end. What's the direction of VB? Same. It's perpendicular to the rod for the same reason. The same equation applies. VB, but its magnitude is greater than the magnitude of VA because the magnitude of this term is greater. This term is the same for both. Actually, the magnitude of the velocity increases linearly with this, the magnitude of this. The magnitude of the velocity of a point increases linearly with respect to its distance from the fixed point. Okay, so technically here my velocity is 0, and as I go, the tip of the arrow is going to increase linearly. So my VB actually is this. And the velocities of all the points are, now I can draw them like this. They are perpendicular to the position vector from the fixed point to the point, and their magnitude increases linearly with the distance from the origin, or from the fixed point. Here, that's the origin. Okay. Let's do a small exercise. Can you draw the velocity profile of this shape? It's a disk also rotating about a fixed point. So maybe find the velocities of several points on the disk. Omega is this way. Draw the velocity profile, the velocities of several points on the disk. Go ahead, please work on this. Omega, yeah. Well, yeah, it's going like that. You can just use the equation to find the direction of the velocity. It's going to be perpendicular to the position vector from the fixed point to the point where you're trying to find the velocity at. And then points at the same radial distance from the fixed point, they have the same velocity magnitude.
Is this for the rod? Is it linearly along the length of the rod?
Yeah, I took several points along the length of the rod, and then I drew their velocities.
Okay, so not like along the
I'm not sure what you mean. Oh, that vector along the rod, that's the position vector to point A. So, but the velocities are the ones that are perpendicular to the rod. So maybe I'll help you out. If I'm looking at this point, this is the position vector from the origin to this point. The velocity is going to be perpendicular to that position vector. Okay? And its magnitude is going to be proportional to the distance. So if I look at other points on the same line, these are their velocities. Perpendicular to the position vector from the origin to the point, the velocity is perpendicular and then proportional to the distance. Okay? And if I look at points at the same distance from the fixed point, then they have the same velocity. Okay? Points at a smaller distance have a smaller velocity, and so on. not the best drawing, but do we understand kind of what's going on? And if I look at a point that's like farther from the origin, its velocity is going to be bigger. So here kind of that's the point with maybe maximum velocity. Okay. So it's very interesting to know, or in rigid bodies where you have a fixed point. Well, first, any questions? Questions? Because some people were having trouble. Yes.
Can you explain that using the formula?
Yes, for sure. Great question. So if I look at point here A, okay, and O. O and A are two material points on the rigid body, right? So I can write that VA minus VO is omega cross RA minus RO, or XA minus XO. Deal? Okay. What is VO? 0 because it's a fixed point. Okay. Omega is along EZ, or here it's minus EZ. It's some scalar along minus EZ. And XA minus XO is this vector. Maybe I'll get my blue chart. Oh gosh. That's XA minus XO, right? So we know that VA, which is omega cross XA minus XO, because of the cross product, VA is perpendicular to omega, so it's in this plane, but it's also perpendicular to XA minus XO. So that's why VA is like that. Okay? And if I were to look at point B, for example, point B also, its direction is perpendicular to XO minus XB. XB minus XO. However, its magnitude, the magnitude of XB minus XA, let's do that. VB minus VO is omega cross XB minus XO. Okay? VO is also 0. Omega is the same. If this has bigger magnitude, then VB has bigger magnitude. The magnitude of VB is linearly proportional to the magnitude of this vector, right? So that's what's happening here. The velocity at point B is slightly greater than the velocity of point A. That distance, that magnitude of B, and then is proportional to this distance from O to B. Does that make sense now? So points at the same distance from the origin, they have the same velocity magnitude. And points whose position vectors are along the same line have the same velocity direction because they're perpendicular to the same line. Does that make sense? So actually having a body rotate about a fixed point is valuable in that we can easily imagine the velocity of the body. If omega is in the opposite direction, you can imagine how the velocity of all points on the body are. However, it's not the case that all bodies rotate about a fixed point. However, there's something that we call the instantaneous center of rotation. Oops. It's also known as the IC. And what it is it's a generalization of the concept of a fixed point rotation to any body that's moving in like general motion. Here we're considering general plane motion. So the idea is, say I have a rigid body. And I know the velocity of 2 points on the rigid body. Let me consider A and B. Let's say that VA is like this and VB is like that. Say I have a rigid body and I know the direction of the velocity of 2 points on the rigid body. Okay, the IC is a point at which the body is instantaneously rotating about. Instantaneous center of rotation is a point at which the body instantaneously meaning that at the particular instant you're looking at, the IC has the same properties as a fixed point. Okay, and then how do we find the IC of a rigid body? We backtrack from the velocity profile to find the IC. So remember, if I have a velocity VA, then if I have a fixed point rotation, the fixed point needs to lie along the perpendicular to VA that passes by point A. If this body is rotating about a fixed point, then the velocity of A, the fixed point lies on a line that's perpendicular to VA passing by A. And the same applies for VB. If this body is rotating about a fixed point, then the fixed point lies on the perpendicular to VB passing by point B. So this here is our IC. And we can write that the IC acts like a material point on the rigid body. Okay, so I can say that VB or VA minus VIC is omega cross RB minus RIC or XB minus XIC. And VB minus VIC is equal to omega cross XB minus XIC. Does it kind of make sense how I drew the IC? So the IC, the instantaneous center of rotation, has zero velocity at this instant. But it's not like a fixed point, its acceleration is not zero, because at a different time, the IC is at a different location. So the acceleration of the IC is not zero. It's not a total fixed point, but it's a fixed point at this instant. At this instant, its velocity is zero. And then sometimes it's helpful in solving the motion of a rigid body. You never need to use the IC to solve a problem, but sometimes it's helpful. Okay? And knowing the IC, we can reconstruct the velocity profile of the whole rigid body. So if I take, for example, some point C here, I know VC is like that, kind of VC. And I can take another point and I can find the velocity profile. And then I can imagine kind of how this body is rotating about the IC. Does that kind of make sense? Yes.
So have two velocities parallel to each other.
If the velocities are parallel to each other,
we will use the linear correlation.
wait. If you have kind of the velocities of 2 points like this, and like that, and they're parallel to each other, you need to know their magnitudes to figure out the IC. The IC is here.
Right, so we're using those profiles.
So here we did not use the magnitudes of the velocities because they weren't parallel. But here you need to use the magnitudes if they're parallel. Or you need to find the velocity of some other point to be able to find the IC, say. Does that answer your question?
Yeah, I have a different question. If we have a rigid body, right?
Mm-hmm.
And we have like 2 points
Mm-hmm.
that are not on the same axis, right?
Mm-hmm.
They are moving with different speeds that are not like equally correlated to each other. So
Mm-hmm.
like.
Do they belong to the same rigid body? Do they belong to the same rigid body, the 2 points? They are material points on the same rigid body?
Yeah.
Then their speeds need to be correlated. Their velocities need to be rated by this equation. Otherwise, the body is not rigid. So the body being rigid constrains the velocities of the particles. Let me give you an example. If I have a rod like this, and I have 2 points, A and B, with velocities VA, could VB be like that? Is that physically possible? No, why not? Because what would that mean? Yeah, that it's compressing, kind of basically. This point is going in and this point is going out. If I look at the projections of VA and VB along the rod. Because of the rigidity of this body, the projections of VA and VB along the rod need to be equal so that the rod is neither extending nor compressing. So the fact that the body is rigid constrains the velocities acting on the rigid body. I have another question for you. If I have a body that's just translating, but where is the IC of this body located? If the body is just translating, where is its IC located? Instantaneous center of rotation. Well, it doesn't have an IC. It's located at infinity, guys, right? Because it's at the intersection of all these parallel lines intersecting at infinity. Okay? Let us see if you really understood this by doing some examples. Show screen. Oh, that's nice. This is a crank slider. You probably will take some mechanics of machines course in your curriculum. You look more into machines like these, but you already know a lot about them from dynamics. So this is a crank slider. What happens is that this disc is rotating, and then the rotational motion of the disc is connected to a translational motion of the bar. Okay. What kind of motion is the disc undergoing? Yeah, fixed point rotation, right? What about the crank? Well, let me ask you an easier question. What about the slider? Oops, the slider, this block. What's happening? This block, this slider. Gosh. Rectilinear, right? It's going back and forth. What about the crank? The crank, it's the one that connects the two. Ooh, what happened? Okay, one more try. If not, I'll draw it. It worked when it matters, so we're grateful. Okay. No, it's not working. Okay. Never. A word? Go. Okay, I'll wait for 5 seconds and I won't touch it. In the meantime, maybe I'll draw it here. Ooh, nice. Okay, this is the... Okay, that's what's happening. We have a disc, fixed point rotation. I'm going to assume that the slider is here. And this is my crank. At one end it's pinned to the disc, and at the other end it's pinned to this. find the IC of the crank. So again, the question is find IC of crank. Okay, that's probably bad for people with seizures and not. Okay, so find the IC of the crank.
This end of the crank has velocity.
So can you find the direction of the velocities of 2 points on the crank to find its IC? Think about it.
At this instant, it's going to be like this. The center of that circle of the crank. Yeah. So it's going to be like. I mean, it's going to be different at different instances, right?
Okay, passing around, yes. And then what is the direction of this vector? Yes.
So I think I understand that the crank is going this way. This is the fixed point connected to the piston, which is going rectilinear motion. This is doing curvilinear motion. But you said before that you can't have.
Wait,
I guess those
the disc.
those vertical, those horizontal components have to be set.
Yeah. Well, the disc is rotating about a fixed point.
Yes.
So what is exactly the direction of this velocity?
Exactly.
No, not one instant. Okay, so let's correct this. So this is my bar over here, or actually, this is my bar over here. The velocity of this point is horizontal, right? This point belongs on this and this, so it's horizontal. What about the velocity of this point? This point also belongs to the disk. The disk is rotating about its center. So for the disk, this is the IC, and then this is the direction of the velocity of this point, perpendicular to the disk. So I can find, say, point A, point B, and then I can extend them. They're perpendiculars at the point itself, and that's the IC. And when you have a motion in the opposite way, the IC is going to be down. Questions? Does that make sense? Okay. Let us try to solve problem in set 16. Yeah, set 16, problem 1. Did you solve that in, well, you didn't solve that yesterday, did you? Did you solve any of these problems yesterday in the exercise session, the discussion section? Definitely not the first, because you didn't learn about ICs yet. Yes. What is it? Not of set 16, because I gave them out on Tuesday, but I have set 17. Okay, so please work on set 16, problem 1. This I can. Okay, so I have this bar. The ends of the 0.4 meter bar remain in contact with the respective surfaces, and B has a velocity of 0.5 meters per second and an acceleration of 0.3 meters per second squared, if in the directions shown. Determine the angular acceleration of the bar and the acceleration of end A. We do not need to use the IC to solve this problem, the concept of IC to solve this problem, but let us try to use it. Let us try to figure out where the IC of this rod is and see if that's any help solving this problem. Okay, so where would the IC of the rod be? Yes?
Like you make the lines perpendicular to each of the surfaces because the velocities just go along the surface.
Exactly, so VB is along this incline and VA is, well, is VA pointing down or up? Down, right? Down, so that's the perpendicular to VA, that's the perpendicular to VB. I'm very clear that these are perpendiculars, and that's my IC. Okay, can we find the location of this IC? We're gonna need to find some angles. What's this angle? $45, right? Because it's 105 plus 30 is 135 minus 180 is 45. That's 45. What about this one? What is it? 45. This one. This one. Yeah. Okay. Well, I know that VB minus VIC. What do I need to find? Omega? Is that what I need to find? Oh, the angular acceleration. Okay, wait. Let's do just omega. This analysis, the IC does not work for accelerations because we know that this point, the IC at a different time is going to change. So this does not work for acceleration. So we're just going to find omega. Find omega. Okay. So VB minus VIC is omega cross XB minus XIC. Okay. What is the velocity of IC? 0. And the velocity of B we know. If I take my basis, EX and EY, VB is 0.5. And what is its direction? What is this angle that the velocity, well, that it makes with the horizontal? What is this angle? This is 90 degrees. What is this angle here? 15. So what is this angle here? Okay, so what is the direction of VB? There's a small mistake in there. Minus the EY. Okay, that's VB. And omega is along EZ. What about XB minus XIC? Can I find this position vector? What is the length of this? Let me call it D. How can I calculate the distance D? And I'm going to need to use geometry, maybe sine rule, cosine rule, sines, cosines. How do I find D? I can do either law of sines or law of cosines. I can say that if I use the cosine law, D squared is equal to what? Well, no, I cannot use the cosine law. I do not know the other lengths. I can use the sine law. Sine, well, D, sine 60 over D is equal to what? Sine 75 over 0.4. Okay. So then now XB minus XIC has length D and has direction. Okay, this is 15. What is this angle here? Well, more angles. If this is 75, this is 15, 90. This one here is 75. So xb minus xic is that vector. It has negative x, negative y components, so minus cosine 75 ex plus sine 75 ey. Is that right? So I can do these cross products and I can solve for omega. How can I solve for omega without referring to the IC? Some ideas? Any equation I can apply? Maybe just VB minus VA. And I know the direction of VB, I know the direction of VA. Maybe I'll just do VB minus VA, so omega cross RB minus RA, and I can find omega. Okay. Let's continue to a new topic related, rolling and slipping. And here there's a kind of naming difference between O'Reilly and Miriam Craig, the textbooks. So according to O'Reilly, he'll use rolling and sliding. And to mean the same thing, Miriam and Craig will use roll without slip and roll with slip. Okay. Consider a disk on some surface S. So we have a disk on some surface S. C is the center of mass of the disk. P is the instantaneous point of contact between the disk and the surface. Oh, that's O'Reilly's textbook, the dynamics primer, and MKB is Miriam Craig and Bolton, the other textbook. So that's just like same wording to refer to, well, different wording to refer to the same thing. Okay, so we have a disk that's on a surface. And I'm gonna call the center of mass of the disk C, and point P is the point that is instantaneously in contact with the surface. If the disk is instantaneously in contact with this surface, or is in contact with this surface, then how is the velocity of point P restricted? Restriction and Vp to maintain contact with the surface. What is the restriction on the velocity of point P so that the disk remains in contact with the surface? Yes. Totally, does it need to totally equal 0 or 0 in a certain direction? Yeah, let us think about, well, maybe you all have cylindrically shaped objects on your body, on your desk. So this is point P, the point that's in contact with my surface, right? If I'm moving like this, am I maintaining contact with the surface? Is the velocity of point P 0? No, but it's 0 in a certain direction. Which direction? Normal to the surface, right? Was that what you were going to say? So if I consider a tangent to the surface, a normal to the surface, Vp dot n is equal to 0. Now, going back to your friend's question, when is Vp totally 0 if I'm rolling without slipping on the surface? So if I'm like rolling without slipping like that, then the velocity of the point in contact is instantaneously 0. Does that make sense? So I'm basically rolling about this point. What I've heard it say that how Miriam and Craig define the rolling without slipping is that you can imagine this being dipped in paint. And if it's rolling without slipping, then as it's rolling, the paint is being deposited on the surface. So however much paint is being deposited is however, so from the circumference is however long you're traveling on the surface. Kind of something like that. If I have the disk, and I have some paint on the surface of the disk. This is radius r, angle theta. What is the length of this segment? R theta, right. So if it's rolling without slipping, then after the disk has come to here, all of this paint would have been deposited. So I would have traveled a distance x is equal to r theta. I don't think. It's more of a geometric meaning. But according to O'Reilly, what we say, and which is true in both cases, is that if the disk is rolling without stepping on the surface underneath, then its velocity matches that of the velocity of the surface underneath. So if the disk is rolling Vp is equal to 0 if S is fixed. If S is moving, then Vp is equal to the velocity of point on S. You can think of a cylinder on a truck bed. We're going to do that problem. We're going to solve that problem. A cylinder on a truck bed. So as long as the velocity of point P is the same as the velocity of the truck, then you're rolling without slipping. The cylinder is rolling without slipping on the truck. If there's a slip speed between the truck and the cylinder, then the cylinder is slipping. Okay? Yes.
You're defining motion. It's like Vp equals 0, right? So it's like not rotating. It's like if it would like move on ice, right? So.
Okay. So instantaneously at this instant, the velocity of point P is 0, but its acceleration is not going to be 0. because say it's rolling like this, the acceleration is going to be purely vertical. Actually, let us solve this problem. Okay. Again, let's look at a disk of radius r rolling without slipping. Angular velocity omega and angular acceleration alpha. I have P and C. Vp minus Vc is omega cross Rp or Xp. Actually, let me do the other way around. Let me do Vc minus Vp is omega cross Xc minus Xp. Okay. It's a very tricky situation, so focus with me a little bit. Is P a material point on the disk? And I defined P as the point that is instantaneously in contact with the surface. The point on the disk that is instantaneously in contact with the surface. So is point P a material point on the disk? No. It's a point that's moving on the disk. It does not belong to its material. If you were to follow the point that was in contact with the surface at this instant, at another instant would be here. It wouldn't be P. So P is not a material point on the disk. So that makes our analysis a little bit tricky. For our velocity analysis, we're going to consider the point that is the material point that is at the location of point P. So the material point that is instantaneously here has zero velocity. However, I cannot take the acceleration of point P as the derivative of Vp like I normally do, because point P here is not a material point on the disk. It's the point that is instantaneously at a certain location, kind of thing. Now Vc, I can write it, the velocity of point C is purely rectilinear in this case. So I can write this as x dot Ex. And omega is omega Ez. Xc minus Xp is taking my basis, regular Ex, Ey. Xc minus Xp is R Ey, right? Which is equal to, what is Ez cross Ey? Minus omega R Ex, so I can project along Ex. X dot is equal to minus omega R. Okay, this is what we will be doing. This is what you will see in solutions in Miriam and Craig. They will use x dot, differentiate this is equal to r theta dot. There's a difference, there's a sign difference between the two. That's why if you are looking at the Miriam and Craig solutions, you might see a sign difference in the problems. So do not do this, please. Always start from here and find this expression. Okay? Questions so far? Yes. Why the sign difference? Why we have the sign difference? Because here, okay, here omega is positive if I'm going along Ez counterclockwise. So omega is positive like that. But here they're taking it to be positive like this. So the disk is rolling this way to traverse a positive x. So the omegas are different, have different conventions. They're rotating the same way. Here, in this case, omega itself, this value would be negative, less than 0, so the total result is positive. Okay? But how did we decide if omega is positive or not? We have our convention. If it rotates like this along Ez, using the right-hand rule, then it's positive. But here it's more like, oh, if I advance theta this way, then I'm going to move in that. It's more like intuitive, more than very rigorous or very, this is more helpful when you're going to deal with more complicated problems. like for example the cylinder moving on its rock band. Now I can take this expression and I can differentiate it and I can find x double dot is equal to minus alpha r. No problem differentiating a scalar equation. And then I can say that VC or AC minus AP is alpha plus RXC minus XP plus omega cross omega cross XC minus XP. So again, P is the material point that is located at this instant at point P. AC is X double dot EX. AP, I do not know what it is. Alpha is alpha, easy. XC minus XP is the same, minus omega REX. REY. And then this is plus omega EZ cross minus omega REX. Minus alpha REX minus omega squared REY is X double dot EX minus AP. With me so far? And then if I use the fact that X double dot is equal to minus alpha R, what will happen? If I use this fact, what will happen?
Also, AP will equal to omega squared R.
Right. AP will be vertical. So that's the acceleration of the material point that is located at point P at this instant. Any questions? Okay, let's do some problems. We'll do them as a quiz problem basically. Okay, there are gonna be two quick problems from set 17, problems 1 and problem 3. Set 17, I have a few copies here, problems 1 and problem 3. So basically these are two wheels, one of them is rolling without slipping and the other problem is rolling with slipping. Okay, that's a pair work quiz, so you feel free to work with your neighbors. I'll give you answer booklets and you'll be submitting one paper per pair. Yeah, try to have pair work, not more than 2 if possible. 3 if really necessary. You're welcome. Do we all have papers?
Can I go?
Sure.
God forbid anyone
So we have two pairs here. Okay, you'll be separating one paper. You can use the other one as scratch.